Here we have another problems, drawing resonance structures and finding the resonance hybrid after doing the assessment of the different resonance structures. So let's do complete the lone pairs. I do that always so that we know we have electrons here. And now another analysis that we can do here, we have a carbon with a positive formal charge. When you have that scenario, we're going to say that that carbon is sp2 hybridized, but we're going to have an empty p orbital. But that is actually, we're going to say this is sp2. Of course, you have a double bond, sp2. That oxygen also sp2, so that we have all of these parallel p orbitals, and we can have electron delocalization. It's like having, when you say that all of those are sp2, it's like you're saying you have this with the right symmetry so that you can overlap here, and their meaning electrons are delocalized. So sp2, 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 sp2. This, however, watch it, this is sp3. That terminal carbon has 3 hydrogens. So, so I need to erase that. So no, I have 1, 2, 3, 4. 1, 2, 3, 4. That was correct, but then I have another that is actually sp3. So that's the idea. In recognizing patterns, several things. If you have one pattern is lone pair adjacent to a positive, I can do a resonance structure that will put a double bond here. When I do that, let's draw the hybrid. So I'm still gonna have the double bond here at the end, and I'm gonna have an oxygen with one lone pair, and we're gonna have a double bond here, and that's it. But now, since oxygen now, notice, has 3 bonds in one lone pair, that's formal positive. So that's one structure. And what else can we do? So if we say from that structure, let's say starting here, I'm gonna do another possible movement, which would be doing this. And let's see how that contributes to the hybrid. So drawing the structure that result with the blue arrows here, I am going to have the following. Let's see. Then we will analyze whether that contributes significantly or not. Here I am putting a lone pair. Of course, charge is going to be negative. I'm going to have a lone pair, so that is positive. And this structure does not contribute. Why is that? Incomplete octet, same as here, but here you have too many charges, plus you have two positive nearby, so I'm going to cross that. So in a way that can happen. Now, I'm going to do yet one more thing. Well, no, I guess that's it. If I move over there, let's say that I do another movement, I can visualize. Probably need to draw it again. Or maybe I'm going to do it from here. Let's say that I do this. And if you do that, here, octet, you have way too many bonds, so I'm going to have to do this. Again, because you don't want to be expanding the octet as it is. This structure octet is complete for oxygen. So notice that you have 2, 4, 6, 8 electrons. So if I move those electrons over, I need to move those as well. So the structure would be, let's see. I will have a double bond here. Since I'm removing those electrons, I'm going to have a formal positive. Now I'm going to have still 3 bonds here for the oxygen, and then I'm going to have this. So way too many charges, as we can see. So net charge, also notice plus 1, but here you have, say this to cancel out plus 1, but this again, too many charges. So the structure that contributes more to a hybrid, so the fewer the charges, if you have a structure with no charge an octet is complete for every atom, that's the best. But also you can have, so the most important as a factor that you need to be analyzing is the octet rule. So analyze what structures have the octet complete. After you've done that, you do the analysis with the charges to assess the resonance structure. Finally, if you do have charges, is you prefer to have the negative charges on more electronegative atoms. So now let's do the analysis. These two do not contribute, as we can see, too many charges. Now, this structure here, at this carbon octet is incomplete. So, and that's the main factor that we're going to be analyzing when assessing resonance structure. Octet incomplete. Everything else octet is complete. Now, in the structure here, let's call this A. This I'm going to call B, and essentially that's it. In this structure, octet is complete in all of the atoms. So notice here you have all of that is complete, and even for the oxygen, you count 2, 4, 6, 8. So all atoms, for all atoms, the octet is complete. It's actually the structure that contributes the most despite of having a positive on an oxygen. So the criteria of the octet supersedes everything else. So because of octet being complete, that's the structure that contributes more to the hybrid. So if you were to draw the hybrid, then it'd be closer to that. So you can have this, and yes, partial here. And yeah, you will do partial when you do this one here from the, I'm going to erase the little arrows for a minute. Just focus on the pink one that is actually originating the structure. And I'm going to be erasing those. I'm considering only those two, the structure. What I want you to see is that the side same, and that I have a partial double bond here, and I will have a partial positive and partial positive. So where is the most the larger, say, partial charge? Actually is in the oxygen, because in this structure octet is complete. So I'm going to draw this delta larger than that, signifying that this structure is the one that contributes the most. Now let's go over the structure in the bottom. What do I have here? Again, pattern. Two atoms, they're joined by a double bond. They have different electronegativities, so I can do this. So my first resonance structure is the following. So I'm going to have, by the way, I'm going to add the lone pair here. I always want to keep track where my lone pairs are. And here, because of that movement, now you're creating this structure with a negative charge and oxygen. Here, I want you to notice this carbon is sp2, 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 sp2. This is sp3. So we're not touching that. Okay, so that's one possible structure. But also I could do, I'm going to do two movements at a time. I'm going to do this, and I'm going to do this. I could have done it in more steps, say. But I'm going to get where to a structure that contributes more. Let's see. What is that structure? I'm going to do a double bond here. And now I have moved over those electrons over here. And now the oxygen stays with the lone pair. And that's sp3, stay the way it is. So now I have two structures. These are the structures that contribute the most. Notice that here, octet is incomplete. So it doesn't contribute much. Complete. And now charge on carbon, negative charge, in too many charges. Plus and negatives, they cancel out. Total charge is negative, but octet incomplete plus too many charges. Now I am between this structure and let's say A and B. Those two. between these two, which one will contribute more to the hybrid. So here, octet is complete. This carbon will have two H's, and so you will have all of the 8 electrons around that carbon. Here again, the same. So octet is complete everywhere, but we're having a negative charge on a carbon. But the octet is fulfilled. Here, octet is complete, and also I'm talking about that as this label is for this structure. So octet complete for all the atoms. Here, octet is complete. Right? But now analyzing that factor is the same, but here I have the negative charge on an oxygen and here on a carbon. So this is the highest contributor to the hybrid. So I'm gonna erase something up here so that we can draw the resonance hybrid of the molecule below. So let's erase the previous problem. And now what's left is just drawing the resonance hybrid. So I am between the structures A and B. So I'm gonna draw, say, the skeleton says, and I have an oxygen, the skeleton, all the sigma bonds stays the same. But now I have, I'm gonna put partial negative here, partial double bond, because notice here I don't have a double bond, but here I do. So in the next bond, here I have a double bond, and here I don't, so it's gonna be partial double bond. And now for the next one, it is no double bond, but here there is. So I'm gonna do partial, and same with the oxygen, double bond here and single, so partial. So electrons are delocalized in all this region that has the dotted lines. And now the oxygen has a delta negative. However, we said this structure contributes more because the negative charge is on oxygen. So what I'm going to do now is put this delta negative larger, signifying that really we will have more negative charge on the oxygen than on the carbon, because oxygen supports better a negative charge, being more electronegative.